And this is a rarity in any conference, I think. I'm going to announce a second Humboldt professor. And this happens in Munich, in Bavaria. I'm proudly presenting this. Stefanie Jegelka is a Humboldt professor at the Technical University of Munich. She came to Munich from MIT, and she has been working on several interesting topics of machine learning, including optimization and deep learning theory as well. We are going to have a very exciting next session. Unfortunately, we won't be able to take questions also, like in Daniel's case, after her talk, but please feel free to try to find her afterwards in the speaker's corner. Thank you very much. Stefanie, please.
All right, thank you very much for the introduction and for the invitation to speak here. It's been very exciting. And in fact, the previous sessions and even the previous talk already showed that multimodality is actually a very important idea in modern AI systems. We have so many different modalities of data. We want to leverage them. And so this is where sort of I want to start with my talk. And I want to show you some ideas. Of course, there's a lot of work. There are a lot of questions, so I can't cover all of this. So I want to show you some ideas from our work, how you could leverage multimodality in different ways. So this is joint work with colleagues and students from MIT. That's acknowledged here. So why multimodality? Well, of course, we all know that when a human learns, there's a lot of modalities that we get. We get voice, audio, we see, we touch, and so on. So we learn like in a multimodal fashion, and it's useful. And as we have seen in the previous talks, that multimodality, of course, goes beyond human learning. We have a lot of different sources of data, and ideally we would like to integrate them, that we can leverage these types of data across modalities in many, many different areas. So we have multimodality everywhere, but one thing I want to think about is like, why is it useful? Why is it useful to do this? Like from a machine learning perspective. So one way to view this is that we have some ground truth reality. You have the patient or you have this scene, and different modalities essentially are like different views of the same thing. So you may have the computer vision, the image that is taken, it sees the cone and the red circle, or you have a text describing that scene, which may actually mention some aspects that are not visible in the scene. So there are multiple aspects to that. The first thing is there is shared content. So both of these views are about the same thing. So I can align, then I can leverage that to get more information about that same thing. So it's more robust. The second thing is some of these modalities may actually give me complementary information. There are certain things that are in an image that are likely maybe not in a text describing that thing. And the other way around, the text may have some information about general things that are not in the image. So I may actually want to leverage that complementarity in the information. So how do we typically leverage multimodality? One way to do this is via aligning data. So this is a clip-style alignment with contrastive learning. So maybe you have images, you have captions of these images, and you tell the model, so the embedding of the image should be close to the embedding of the text. And then you train this. And it actually gives you a model that sort of can reason across these modalities and sort of knows like which text belongs to which kind of visual information. So this has been leveraged in many, many models. It's a common approach, and it works really well. There's only one drawback to this, and that is that this kind of approach, I'm assuming I have the image and I have the caption. And I'm aligning the caption with the image. Data point, like so for each data point, I have these two views, and I know they are the two views of the same data point. Now, in reality, very often, that's not the case. I have some images, I scraped them from somewhere, collected from somewhere of another database that has text descriptions of patients, of other things. So, but we don't know like that a specific text data point corresponds to a specific image, for instance. We don't have that pair. So we can't really do this, because here we really know, like, I don't know which thing align to which one. I know they are somehow about the same thing, but I don't know, like, exactly per sample which belong to the same thing. So what do we do? This is the problem of basically having paired data versus unpaired data. And in my talk, I will mostly focus on the case of unpaired data and ask the question, is that unpaired data still useful? So now I have like some text and I have some images, but I don't have the one-to-one correspondence between the two. And if I could leverage this, the advantage is there's a lot more data that is not paired than there's data that's actually paired, like actual images and captions and so on. So this goes beyond just vision and text, but this is sort of the example modalities here. So what to do? Is it still useful to have that, the right-hand side? So I want to show you in my talk 2 ideas how you can still leverage sort of just these 2 databases of modalities or more of them without having the paired alignment between them already. And if I have time, I'll talk a little bit about sort of like cross-modal correspondences as well in multimodality. So but let's focus on the first 2. First, I'll think about like why is it what kind of useful information could be there in this other modality, and how could we leverage it? And then I'll talk about another idea how to leverage like multimodality in generative models. So let's look at a general representation learning approach for unpaired multimodal data, and why could it be useful? And this is joint work with my student Sharut Gupta. Okay, so question is, can unpaired data be useful at all? So imagine you have this image classifier, whatever it tells you about what species of butterfly you see there. And you train it with some image classification objective or something like that. So now imagine you had another modality, which is text. So this text doesn't relate to that particular image. It doesn't tell you it's that type of butterfly, but it's generally about butterflies and also about other things. And now you could train, of course, a model like doing some encoding of that text. But is that useful at all for your downstream task about image classification? So for the moment, you don't care about the text. You want to do as well as possible on the images. Can this text help you at all? And the idea is maybe there is actually some information in the text that's complementary to the information in the images. They are fundamentally about the same world, so maybe there's still some information in the text more generally that tells you about concepts, general information about, say, the concepts, classes, tendencies, etc., that also relate to the visual world. So maybe it tells you that the viceroy resembles the monarch, but has a certain line in the hind wing, and that may actually help you. So maybe it actually can help you. So let me first try to formalize this a little bit in a simplified theoretical setting, and then we'll go to empirics and see whether it actually can help us. So let me model this, and so this is like a little picture of it. Let's say we have this ground truth reality. There's sort of some theta describing the underlying real world. And now we take different views. We have maybe the visual view, and we have a text that talks about, so different modalities that are sort of derived from the same underlying ground truth. But the way they are derived from that ground truth is that they both capture joint common information to various extents, and then they have some modality-specific information. Okay, now we want to learn something, let's say, about this shared latent information. So it's maybe the class or like what kind of bird this is or so. Does it help to include the other modality if I just have the image? So from a statistical viewpoint, you can show that under certain conditions it actually can truly help you. And the idea is basically, again, that there is some information in the text that's relevant to, say, the shared information, like whatever the type of bird or so, that is not in the image itself. So for instance, this is a passerine bird, and it's native in Eastern North America, whatever, like something about the bird that's not directly in the image. And it can actually help you, it can decrease your uncertainty about that information. So you can prove this. I don't want to go into the details of the formality, but reduction in variance means, in the estimator, means you're more certain about your estimation. Here it says, like, basically the measurement has to be full rank. You can say basically there are certain directions where, say, maybe my images or one modality doesn't give you a lot of information. It doesn't measure them very well, but sort of the other modality can help you fill the gap. That's the main idea, and then you can formalize it. So what this also means is there are cases where it can actually be helpful, instead of having more data from one modality, to actually have data from the other modality, because it gives you information where one modality doesn't give you that much information. So here's a very simple, like, empirical illustration of this, where we have X and Y are like the different modalities. This is a simple Gaussian setting. I'll show you the real one in a minute. And basically what it shows is if I get more of the X data, the pink line, I get only so far. But if I actually get X and Y data, so the two different modalities, the two different views, I can do better. So what this means is I have these two different modalities, and I'm actually trying to estimate the same thing with these. So the way this is here in this simplified model, what we are doing here is basically we have that shared estimator. In this case, it's a shared encoder and decoder. So we have some shared backbone that combines the information. And this is something you can do even without paired information, because they sort of either this one goes in or this one goes in, and you just train the same model with it. That's sort of where the information is shared. So it's less explicit in alignment. It's just I'm training the same model once with one modality and once with the other. So this inspires like a more real-world model, not only for Gaussian data, which looks roughly like this. So the main idea is we have that shared estimation of the same thing, which is basically a shared backbone. And then you have modality-specific projections, and you can also have decoders, whatever. You can have an image objective and a text objective, if you like. But the important thing is we have the shared model. So basically, the idea is very simple. It's like, OK, we are trying to learn something about this real world. So it's basically like a foundation model, but we have that shared backbone. Sometimes we feed in images, sometimes we feed in text, so they don't have to be paired. But you actually can get benefits sort of ideally for both modalities, because they complement each other. So it's not an explicit alignment. It's more sort of sharing basically the weights. So does this work? Let me show you some examples. This is not medical data. This is just image, etc., benchmarking, but just to show you that it works. So this example is sound classification. So in this data set, you have sound from clocks, and you have images, and you also have text. So if you just use the audio and you train a classifier on the audio, that's the green bar. You see it gets sort of somewhere. If you add another modality, these are the blue bars, you actually get quite a big improvement just by sharing the information across the modalities. And this is unpaired. Here's another example. So one thing is it helps you in performance in distribution, but another thing that it can do is it can help you in robustness out of distribution. Because again, maybe one modality covers sort of one aspect, and if you see more data, you just cover a wider range of scenarios, and that'll help you in out of distribution robustness. So in this case, the target modality again is vision, and we augmented it with text, and with the text augmentation, it was actually much better in out of distribution robustness. Here's some visualization. So you may wonder, okay, like, what does it actually do? How does it work? So I have like two illustrations of getting a little bit of an intuition. So this illustration is from, it's classifying cats, but it sort of illustrates how does the decision boundary change if we add the text modality. So this is for the image classifier, but now we also feed text through that same backbone. On the left side is when we just do a unimodal model. There's that one cat that it misclassifies because it's by visuals, it's not so clear, like it's somewhere in between. But if you add text information, so again, it's not paired, but you see the text has some general information about these types of cats. it actually helps you to shift the decision boundary because it talks, for instance, about the color. Like on the right-hand side, you want a cat that's gray, and this is obviously not a gray cat. So that makes it easier to classify. So it shifts the decision boundary once you feed the text through it as well. The next thing you may wonder is, well, what is actually being shared? So I have these modalities. Is it like doing a real alignment of the data? So it doesn't really. Actually, even CLIP, it has this modality gap. It doesn't fully put them on top of each other. It just has sort of a predictable correspondence. So it doesn't either like put the modalities exactly on top of each other in the embedding, but it does something with the weights, with the classifiers that is shared. So I don't have a good interpretable visualization about it, but one thing that we observed is that you get what we call multimodal neurons. And this is what you also get when you do alignments like CLIP, is basically neurons whose behavior is correlated across the different modalities. So they kind of learn to detect the same signal across text and images. So they become more and more correlated across the modalities during training. Okay, so we saw that actually multimodal data can be useful even if we don't have directly paired data. So we can just use it to train. Actually, you can do this with self-supervised learning or a discriminative model. We can train a model with a shared backbone that leverages information across these modalities. The next thing I want to show you is how you can also leverage multimodality in generative models. And in this case, what we'll do is we'll actually not exactly use the shared information, but we'll directly leverage specific complementary information. Okay, and in this case, we'll actually even like generate the pairs. So we'll do generative modeling, so we'll use diffusion models. You probably all know about diffusion models. They're like a very powerful methodology to generate everything, basically. Text, images, videos, proteins, whatever. So they are very powerful, but they are also very expensive and difficult to train. So it's basically very slow in training. It's expensive to train them. And one observation that people had is they kind of learn a representation of your data like other models do, and that the quality of that representation correlates with the performance of the model. But the quality of the representation is kind of going slowly. So what this gives is the idea, well, maybe we can actually help these models train faster if we help them with some regularization. We give them some guidance on what the representation should look like. So this has been a successful idea. It has been tried for image generation. And the idea, for instance, here's an example, is the following. You have so the diffusion model itself also uses these transformer blocks. And it has some internal representation. And what you do is you align that internal representation with a pre-trained representation of that data. So now it actually learns sort of what the representation of that image is with some projection, because it's a noisy version of that image. And that guides it sort of towards learning a better representation, and it greatly accelerates training. So this has been very popular. But one thing we were wondering is, so is this idea, or can it do more? So this was for images. Can we leverage this idea across other modalities? Maybe we don't only want to generate images, we want to generate other things as well. The second thing is, so here, of course, once you generate other things, maybe you want to align with, whatever that other thing is. Of course, not only images. But maybe you also, like, there's more you can do to guide it. Maybe there's more information. We saw that multimodality helps. Maybe you can actually exploit multimodality also to help learn these generative models. So where would this help? Would multimodality help at all in this case? So the idea is, yes, you can, of course, try to do this for other things as well. Why not? Multimodality could potentially help you because different modalities give you information at different levels. So if we think about the images and image representation, maybe it has more of the low level, like image structure in it. You could use a vision language model. That's maybe more about concepts in the image, like higher level. So what you could do is you could actually use this in a complementary way. You align the image representation at a lower level. They also aligned it here at a lower level. But as you go sort of deeper into your model, that's a more conceptual representation. That's what you align maybe with your text representation. For instance, things like that. So you could use multimodality to sort of steer different levels of representations of your model to give it, to sort of give it even more information. How would you do this? So what do you do with a diffusion model? You have basically this idea that, well, you have images, you generate noisy versions, and the diffusion model learns the reverse process of this. In addition, you have the latent. That's the auxiliary latent, is this other representation that you're aligning with. So you can put this into a probabilistic model and build a generic model about it. So the first thing we did was we said, okay, like generalizing this idea, you could say instead of having one latent representation, like just this image representation, you can have multiple from different modalities, multiple representations. Another thing you have to think about is how do you want to steer it? So the representation guidance is actually most useful in the early stages of training, and later maybe you want to let it go a bit more freely and like optimize its representations for the actual generative tasks. Finally, you can also be a bit more flexible about where exactly in the time process you insert that information. So because this is going it's flowing backwards essentially, and you can do things there. I'm not going to go into the details, but you can do a specific decomposition, and it basically gives you an objective that combines generation and alignment. And so now in your you can basically trade off how much you want to focus on generation or alignment. Okay, but let's go back to the multimodality, because this talk is about multimodality. So it gives you complementary information. But now the thing is, okay, now we are actually generating maybe this particular image or so. So where does the other modality come from? If we assume that we do not directly have paired data to start with. So we could try to do something more general and do about something about concepts, but maybe here we want something that's really specific to the thing we want to generate. The other thing is if we had paired information, maybe that's already too much information. It'll give you shortcuts or so. So where does this other modality come from? And in this case, we took another approach and we said maybe you can just generate it. So you can use synthetic data. You have a clean representation of the same thing in a different modality, and you could use this. Question is, does it, this is coming from my original image or so, does it actually help? Yeah, we'll see if it helps or not. So we'll use sort of synthetic view of our data to help guide the diffusion model. So let me show you just some examples of what this could look like. My first example goes back to image generation because that's sort of the easiest visual thing. This picture is a bit complicated because I was lazy and I just took it from the paper, but let me explain. So the idea is your diffusion model is supposed to generate an image, and what people did before is you take that image, you send it through some learned representation model, and it gives you sort of the image representation, and you align them. What we do in addition is we use a vision language model to also generate text and use the representation of that text to guide the model as well. Now the text is exactly the thing. It has the higher level information. So if you optimize sort of which layer of the model you align it to, you would align this to sort of a deeper layer and the image representation to a shallower layer. Okay, here it is. So this is a small thing, but basically it shows that image you align to layer 4 and the other one maybe to 8 or so. Okay, does it help? This is the comparison. So if you look at the blue line is sort of the generic training of the generative model. The red line is with one modality and the green line is with two modality. So you actually are faster, so you still gain from the text modality. Maybe the images gain you a lot, but the text in addition actually still gains you something. Okay, so let's look at something else. And to our knowledge, I think we were the first to try this for some of these other modalities. So let's look at protein folding. or basically inverse protein folding, so protein design, sequence generation. So the idea is I give you a structure, like I give the model a structure, some constraints, and the model has to generate basically a sequence of that protein. So input is the structure, output is the sequence. So what are the modalities here? So one modality is an embedding of that structure. The other modality is a sequence embedding, so information about sequence. So in this case, we took it from AlphaFold, so we take the structure embeddings from the diffusion model, and the other ones are the pair and single embeddings that we get from the performer. Okay, and it actually, this works. So here is the table. It speeds up the training by about 3.6% times. So in this case, actually another interesting thing is the alignment. So when you look at AlphaFold, it goes from the sequence to the structure, and what we are doing is sort of the reverse thing, so the alignment is also in the reverse direction. You first align the structure, and then you align the sequence. And that actually, it helps the model train. Here are some example results of the proteins it you generate the sequence, and then you refold it, and you align them with the ground truth, and you see it's actually pretty close to the ground truth. Okay, and the last example is molecule generation. So you can do the same thing here. You have a noisy point cloud, you want to make a molecule, and the two modalities are the 2D and 3D. So 3D, that's the natural one, and the auxiliary one is that you build a graph. You can do this with tools, and you do a multi-modal representation model. You use that to get the different representations. Again, I don't have the speed up curves here, but it actually does perform better than the models without the alignment. So what this shows is basically that you can leverage multimodality for like different generation tasks. It works across different types of tasks to accelerate your training by leveraging that the different modalities have complementary information. So you really use exactly the complementarity to give the model guidance at like different levels, essentially. With this, let me just jump to my last slide. All right, so we saw that multimodal data gives you complementary information. I showed you two ways to use this, with a shared backbone or with the alignments that you can do for generation. So there's a lot of interesting questions there. What exactly is shared? Another thing we worked on that I didn't talk about here is if you look at multimodal representations across different models, they are actually not so different. You can align them. There's a close correspondence between those models, and you can actually align them with like just a linear transformation, which is interesting if you want to do model transfer or efficient training and so on. So I'll stop here. Thanks for your attention.